So this is, looking at number 1, is actually the same one we did Thursday, but I'm just going to do it again. This time it'll be recorded, and you can watch it again and again and again and again. So the idea here with partial fraction decomposition method is just another method for integrating. It's used exclusively for fractions. The name kind of gives that away. It has the name fraction in it, so you're going to use this when you see a fraction. Although we have another technique that handles fractions, if you remember, U-Substitution can't handle a certain type of fraction, right? That's where if you have something on the bottom and it's pretty much its derivative on the top, right? So if you have that, it's better to just use U-Substitution, So that's kind of the basic rule always. If I can do U-Substitution, do it. If not, then I have to do one of these other techniques. And so when I see a fraction that I'm supposed to integrate, my first thought is, oh, please let it be U-Substitution. And I look at it, and this one is clearly not U-Substitution. Can someone tell me why this is clearly not U-Substitution? What's that? Yeah, the top is just 1, and 1 is not even close to the derivative of x squared plus x, right? I mean, it's the derivative of x squared plus x we know is 2x plus 1, which you can't make up for an extra 2x added in there, right? So this is not going to go with U-Substitution. So I have to use some other technique. And right now, the other technique you have for fractions, for the most part, is partial fraction decomposition. Integration by parts sometimes can handle some little fractions, but that's not a common, it's kind of rare, but occasionally there's a few fractions that it can handle. But okay, so I look at this and I think, okay, so what makes you think I could use partial fractions here instead of the other one that I don't know about, or integration by parts? And first of all, you want to look and see if the bottom is factorable. If the bottom's not factorable, then you can't use partial fraction decomposition. It's got to be factorable. Okay? Is the bottom factorable? Yeah, you can pull out an x, can't you? So usually what I do is, instead of having to write that little integration symbol over and over again, I go off to the side here and say, I'm going to play around with this fraction for a minute. That way there's notice I'm not saying that this thing over here is equal to that. I'm just going off to the side and doing some side work. That way I don't have to be careful about what's equal to what. I don't want to keep writing the dx and the integration symbol over and over again. And I know that you guys don't like it either, so I'm helping you out here a little bit. So I write the fraction off to the side, and then I think, where did this come from? What two fractions did I add together to get this? And of course, we base our answer to that question on the concept of the common denominator. So we look at this and we say, what two fractions could I have had that would give me a common denominator of x squared plus x, or otherwise known as x times x plus 1, right? And I would say, well, that's got to come from something over x plus something over x plus 1, right? Because if you had those two fractions, they would have a common denominator of x times x plus 1. Everyone buy that? And so, since I don't know what the top is supposed to be, I put an a and a b. That's what we do when we're not sure what something is. We put a variable up there, and we're using the a, b's, and c's, because remember, a, b's, and c's usually are they're not really a variable because they're not changing. There's some kind of a set value. I just don't know what they are yet, which is different than an x or a y. Remember our little discussion about variables a long time ago? Or maybe that was in Calc 1, so I don't know. I can't remember who I've had that discussion with. I've had a discussion with a lot of people about that. But. Okay, so now once we do this, now we've written an equation that we need to solve for a and b. Right? And of course, anytime I see fractions, I call for the superhero fraction bus stop. Or in other words, I just multiply the entire equation by the common denominator. And in this case, the common denominator is x times x plus 1. So I'm going to multiply everything by x times x plus 1. X times x plus 1. And x times x plus 1. Everything gets multiplied by that. So here they all cancel out. I'm left with just a 1. Woo! That was crazy. Here the x's cancel out. I'm left with an a times x plus 1. And here, the x plus 1's cancel out. I'm left with a bx. Okay? Any questions or comments so far? So this is hopefully looking familiar to you if you were here Thursday. This is the exact same problem I did on Thursday. So now what we do is we try to find out what A and B are. And this is, I talked about this Thursday, but you basically you want to line up the things that are associated with x on the two sides and the things by themselves on the two sides. So over on this side, I have 0 x's and 1, 1. Over here, I have an ax and a bx and an a. See how I just multiplied the a through and kind of got the x's together? So on this side, even to be more specific, I have 0 times x over here and plus 1, and I have a plus b times x, don't I? You see that? If I add ax plus bx, I get a plus bx. So that means, just by look at this, if we understand how the equations work, that means that, and I'll bring some highlighter in just in case we don't know how equations work. That means that this right here has to be equal to that for these two to be equal, doesn't it? Does everyone get that? Because I have a number in front of x on the right, and I have a number on the front of x on the left, and they have to be equal to each other. Otherwise, these two things wouldn't be equal. And likewise, since that's just a number by itself, that's got to be equal to that, doesn't it? So by the power of highlighting, we can tell that a has to be equal to 1, can't we? Let me get rid of my highlighter now, since we're done with that. So that means that a has to be equal to 1, and also a plus b has to be equal to 0. So if a is equal to 1, that means b has to be equal to negative 1. So this is recorded, so you can go back and watch this later, if that'll free you up having to take such copious notes. You got one of those, right? Okay, so then we finally go back to the integral. So now that we got things figured out, and we're going to say, well, this thing is actually equal to the integral of, let's see, a was positive 1, right? 1 over x dx plus the integral of negative 1 over x plus 1 dx. Okay, so I just took those two fractions that it broke into and wrote it as two different integrals. Because if I have an integral of something plus something, I can break that into two integrals, right? So now I can integrate them, and now this is, remember when we first looked at this, we asked ourselves if this is a U-substitution situation, and we said no because the top was not the derivative of the bottom. Remember that? Now we're going to ask that question again. Is this a nice U-substitution situation? Yes. Yeah. Because we found out that b was negative 1. Right? We said a was 1 and b is negative 1. So remember where a and b were. A is the first one and b was the second one. Thanks for asking that. Okay? So now we see that. Oh, that's, I don't even know if I probably don't even need U-substitution for this because I can spot that. If you've been doing a lot of U-substitution, you can spot that clearly as, at least that first one, that's just ln x, isn't it? That's just the if I take, so that's got to be ln x. Why did I write two equal signs there? That would just be ln x. And that second one is not too far from ln x. That's just ln of x plus 1. But there's a negative up there that I don't have, so I'll have to throw a negative in there. So I'll just get rid of that plus and put a minus. And then plus c. And that's that old saying that the hardest part about calculus is the algebra. That's absolutely true of this technique, because you do all the work in this stuff over here where we're highlighting, and if it doesn't produce simple integrals, then that means integration or partial fraction decomposition is not your technique. And that's the whole purpose of partial fraction decomposition, is it creates these new integrals that are really easy to do, and usually when you get back to that point, you're like, oh, that was easy, and you just do it. So, yeah.
Is that the absolute value of x plus 1?
Yeah. Yeah, anytime you integrate ln, I've been sloppy about that. You really should call it the absolute value, because ln is not defined for 0 and negative numbers, so. Okay. Let's look at, what did I say, number 1 and 4. So let's take a look at number 4. Now, the only thing that gets more difficult about this, of course there had to be something that made it more difficult, right, is sometimes we have some unique situations like this. What's unique about this? Okay, that's different than last time. True, this time we won't have to put into 0x, it'll be 3x. But this time also it doesn't have a constant, does it, on top? So we'll have to think of that extra constant as 0, right? So just like on the first one, we called it 0x plus 1. This is going to be 3x plus 0, because we'll have to connect anything on the right side that doesn't have an x with it to 0, right? Okay, what else is unique about this one? Yeah, it has a repeat factor is the way I would say that, but the same thing, it's a square, right? So the first one was able to factor it, but you factored into 2 different factors, right? This one has a repeat factor. That makes it a little bit more challenging. So what I'm going to do, once again, is come over here to the side and say, I'll call this 3x over x minus, what was it, 3? Yeah, minus 3 squared. And I'm going to try to break that into 2 fractions. Well, I know that one of the fractions has to be x minus 3, right? Now this is where it gets a little bit tricky. What would the other one be? Yes. Nicely done. Why is that? That's what you said, right? Yeah. Why do we need a squared on that second one?
Because it wouldn't be the greatest common factor if you only had 2 single ones.
Yeah, if we just had this, great. That was a great explanation, Robert. Thank you. If we just had this, we wouldn't need to square them to get a common denominator, would we? If we just had that, we could just add them as is. We wouldn't have to do anything because they already have the same denominator. So in order to get that denominator, the one that's written over there, we have to have one of them as regular and the other one is squared. Otherwise, you wouldn't get x minus 3 squared as your common denominator. Okay? All right, so, and then other than that, now we're just going to go just as we were before. But this is, of course, a little bit more difficult, because now when I multiply by x minus 3 squared, I'm going to do that to the whole thing. I'll get 3x here, obviously, right? Here I'll be left with an x minus 3, because one of them canceled out, the other one didn't. Yeah? And here, all of them cancel out, don't they? Yeah? So we're left with just a b. Okay, everyone good with that? So again, if you didn't understand, what I'm doing here is multiplying everything by x minus 3 squared. X minus 3 squared. And x minus 3 squared. Multiplying by the common denominator, just like I did last time. In this case, everything canceled out. This case, one of them canceled out, but I left with the other one. In this case, all of them canceled out. Okay, so once again, I'm going to pair up the things that go together. I have a 3x plus 0 on this side, if you will. And you don't have to write that every time. I'm doing that so you can see the connection. And then over here we have an ax minus 3a plus b. So now in this case, if I bring out the highlighting again, the 3 has to be equal to the a, because that's the only thing over here that has an x on it, isn't it? And the 0 has to be equal to all of this stuff, doesn't it? Because none of that has an x. So those guys have to match up. So that allows me, first of all, it basically gives me an answer and it helps me find the other one, because that means that a has to be 3, doesn't it? That way ax and 3x are equal to each other. And then but that also means that 0 has to be equal to negative 3a plus b. But we just said that a was 3, right? So that means that 0 is equal to negative 9 plus b. So that means b is equal to what? 9. Awesome. So we got 3 and 9. So then we go back over here and we say, okay, I'm going to rewrite this baby. And I'm going to say 3 over x minus 3 dx plus the integral of 9 over x minus 3 squared. Oops, sorry, dx. Okay? Now we just got to integrate them. What about that first one? Can I integrate that? Is that a simple du over u? Almost. There's an extra 3 in there, right? So really, if I pull the 3 out, I could write that as 3 times the integral of dx over x minus 3. Whoops. And then that would clearly be 3 ln of x minus 3, wouldn't it? Now this one, it's not quite as cooperative, is it? This is not a du over u. We all agree with that? We might have to pull out the u's to see this one. What if we let u equal x minus 3? Then du would be dx. So then we could rewrite this as 9u to the negative 2 du. Does that match up exactly? Yep, it does. So now we can integrate that, and we're going to have u to the negative 1, and we'll have to make that a negative 9 plus c, and then if we substitute back in, our final answer would be 3 times ln of x minus 3 plus negative 9 times x minus 3 to the negative 1 plus c. Partial fraction decomposition. Any questions or comments on that one? Yes? Go back over here. Is that okay? You have a question about it? Yeah. You good? Okay. Any other questions or comments about that one? Oh, the U-Substitution? So once again, this is there's something unique about this. This one has an x on top and no constant, which is fine. We've already done one of those. That's shocking or surprising. But what is different about this one? It's already factored, which is maybe a gift, right? Because the other ones we had to factor ourselves. Well, actually, that last one was factored too, wasn't it? But yes, it's already factored. But what else about it? Can it be factored further?
Yes.
Yeah.
X squared plus x plus 1 can be factored further? Mm-mm. If there's a 2 in there, if it's x squared plus 2x plus 1, you can factor that into x plus 1 times x plus 1. But that thing's not factorable. And that's what makes this one a little bit more challenging, because I have 2 factors, but one of them is a quadratic factor. Right? So far we've had only linear factors. Yes? Okay? So we're going to have to handle this one a little bit different. So once again, we're going to go over to the side. I'm going to write our big fraction, x over x minus 1 times x squared plus x plus 1. And this time we're going to break it into 2 fractions again, which we're going to have x minus 1. And we'd have to have x squared plus x plus 1 here, right, to get the same common denominator, right? And we are going to put an a here. But when I go to do the second one, I have to consider all possibilities. Now, over here, because it's squared on the bottom, basically our assumption is these things are reduced to the lowest form, right? But on this one, sorry, those of you watching the video, I'll come back over. On the second one, since there's a squared on the bottom, we have to leave in the possibility for there to be an x on top. So in other words, when I write this, I'm going to say bx plus c. Because if my top of my fraction always has to be 1 degree smaller than the bottom of the fraction. So notice in the first one, it's a first degree polynomial, so that means the top can be a 0 degree polynomial. In the second one, because it's a second degree polynomial, the top could be a first degree. It doesn't have to be. I mean, b might end up being 0. But we have to allow the possibility for it. Okay? Now, having just said that, notice up here, I didn't do that up here. Right? That x minus 3 is a quadratic factor, but I only put a b up there. That's because it's a repeat factor. I don't have to do it with a repeat factor. But if it's not a repeat factor and it's a quadratic, I have to build in the possibility of a x on top. Okay? Everyone understand that? Okay. So now I'm going to do the same thing I always do, multiply by the common denominator. And I'm left with an x here. I'm left with an a times x squared plus x plus 1. And I'm left with a bx plus c times x minus 1. Bless you. Okay? Okay, so let's multiply some things out. So I get x equals ax squared plus ax plus a plus bx squared, right? Plus cx minus bx minus c. Sorry, I was going in a different order than whoever said that, but you were right if you were doing it in a different order than I was. Okay? Now we have a lot more players than this one, a lot more confusing things, yeah? So now we got to maybe build some stuff in here. So really what I have, because I have x squares over here, I have 0x squared here plus 1x plus 0, don't I? Again, you don't have to write this, but I'm just kind of helping myself see what goes on here. So then over here, I'm going to have an ax squared plus bx squared. I'm putting all my x squareds together. And I have a plus ax plus cx minus bx. Yeah? And then finally I have a plus a minus c. Okay, so now can you write some equations from this? I know that 0 has to be a plus b, doesn't it? Which tells me they have to be opposite each other, right? I also know that 1 has to be equal to a plus c minus b. Yeah? And finally, I also know that 0 has to be equal to a minus c. Because I didn't have because on this side, well here, I'll highlight it. On this side, I have an, whoops, a daisy. I think there's an undo button. I outsmarted myself. On this side, I have an ax squared and a bx squared, which means I have to have an x squared on this side, right? And then I also have a ax, cx, bx, so then I have to have an x over there, which I did. That was fine. And then I also have a and a c without any x's attached to it, so I have to have something over here with no x's attached to it. So I have to account for everything on one side, for everything. Well, I have to account for everything on the right side over on the left side. I have to make sure that there's matching up, right? So you can see that that blue connection ended up down here, and the green connection produces this equation, right? And finally, the yellow stuff connected this equation. So you see where all those equations came from. Okay? Now we got to use our expert algebra skills to sort this stuff out. Well, I know, let me go back and get rid of my highlighter. Sorry. So let's say that I can tell right now that we could put everything in terms of a, couldn't we? So we could say that a is equal to negative b. Yes? And actually, I'm sorry. I want to do that the other way around. That b is equal to negative a, and that c is equal to a. Just got that from the yellow and the blue equation. Because then I'll come back to this middle equation and say that means that 1 is equal to c plus c. I'm sorry. Stop that. 1 is equal to a plus a minus a negative a. Yeah? So in other words, I'm taking this and subbing a in for there, and subbing a negative a in for there. And so what I end up getting is that 1 is equal to 3a, don't I? Which means 1/3 is equal to a. And we just said that c is equal to a, so that means that c is equal to 1/3. And we also said that b is equal to opposite a, so that means b is equal to negative 1/3. Now we're ready to go back and rewrite my integral. So my integral is going to be, the first one was a, which was 1/3. So that's going to be 1/3 over x minus 1 dx, right? The second one, I'll have this x squared plus x plus 1 on the bottom. And I think I'm going to take the 1/3 out front. I should have done that on the other one too, but just to get the fraction out of there, right? And what does that leave me with on top? Well, I forgot what I called what. So b is negative and c is 1. Yeah. So if we bring out a negative 1/3, that would leave me with x minus 1, wouldn't it? The dx, yeah? Questions on that one? Let me just redo that. I think I did 2 steps in one. Let's go back over here. So we know that b is negative 1/3 and c is 1/3. So what I really have here is negative 1/3 x plus 1/3. Right? Does that look better? And then what I did is pull out a negative 1/3, and that's why I left an x minus 1. Yeah, yeah.
So if we were to pull the 1/3 out of the first crystal, it would just be 1 on the top of that.
Yep, exactly. So we did 1/3 integral of 1 over x minus 1 dx plus or minus 1/3 integral x minus 1 over x squared plus x plus 1 dx. Yeah? I'll just make sure everyone's caught up. You all good at this point? Any questions or comments? Okay, so what about that first one? The 1/3 will go along for the ride. Natural log of x minus 1 minus. That 1/3 also can go along for the ride. What are we going to do with that monster? We could try doing a u. U is equal to x squared plus x plus 1. Therefore, du is equal to 2x plus 1. Uh-oh. We have a 2x plus 1 dx, and we have an x minus 1 on top. That's a problem, isn't it? Shoot, did I create one that's not integratable?
Pull the x minus 1. Oh, leave 1 over.
That was a negative, right? B has to be negative down here? It sure does.